Okay, next we're doing the backward pass. For now, we'll just work on the dense layer first off, and then we'll build our way up. So I got rid of a bunch of what we had started off here, just to make things simple. And let's see, neurons. 2. And then our first example set here, data set, is going to be an OR gate. I just copy and pasted that in there, so you can do that. And then we can go down here. Make the X data and Y data. And then we'll go ahead and populate these two with this data up here. And this is not in matrix form, so you just have to do it the old-fashioned way. Okay, so this code will, the for loop will take this data up here. So it'll go through the rows and the columns. Dimension rows and columns of this, and if j is less than the input dimension, so j 0, 1, these first two will be put into the X data set, and otherwise j being larger than 2, well, this last one will go into the Y data set, and then it'll come back here. These two will go in the X, and this one will go into the Y. And so it creates our X and Y data sets. Alright, so we made the data here. We're gonna go back into this file where we created all our neural net functions. Go back to the dense layer class. And so we made a lot of extra things during the forward pass. Something like weights transpose, derivative of the weights, all that kind of stuff. The layer inputs and transpose. That was all in order to, and the dupe biases. That was all so that we can use these in the backward pass. Yeah, and we allocated these as well. The derivative of the weights being the same dimensionality as the weights. Derivative of the inputs being the same as the inputs. So you can use those to adjust the inputs, so you can use these to adjust the weights. And then these are so you can back propagate through previous layers if you had previous layers. Alright, so we made the forward pass, and now we'll go ahead and make the backward pass. D values here is going to be the derivative values of anything after this layer, because of course the way back propagation works is using the chain rule of the derivatives. So anything forward, anything beyond this, later than this layer dense, will back propagate into this layer dense, and we'll have these derivative values that will be back propped into it. Alright, so and then in terms of the derivative of the weights, so if we go back up to a little explanation here, let's say you have A and B as the inputs. You have C, D, E, and F as the weights, and then O and U as the outputs. So in order to get O and U, we'll take A times C and B times E. So A times C plus B times E. So this way, and then down that way to get the O. And now to go backwards, we will, so A times C, you want the derivative with respect to C. Well, that's just A times C. So derivative of C, if you pretended this was X, AX, the derivative of AX would just be A. So really the derivative of the weights is basically the inputs, and then you multiply those by the the derivative values to get that chain rule effect. So we end up doing, and you do need to transpose these values so it gets back to this shape. But yeah, so, and that's why we have these transpose values here. Because first we're gonna transpose. I almost forgot about that. Go back to matrix ops. Do void mat transpose. Yeah, we're back in the matrix operations folder. We'll go down here. And it's actually pretty simple to transpose. You just go through all the original dot rows. Basically go through all the original values. And you're just going to switch the I and j values. And that will get you the transpose. Save that. Come back over here. On the backward, we're going to do that mat transpose on the inputs, which we saved in layer inputs. So there's the transpose that we'll put it into, and then the layer inputs that we saved in the forward pass as the inputs. You just do a matrix multiplication to get out the derivatives of the weights. Of those transposed layer inputs and the d values that we're getting from future layers. And then if we have a bias term in there, that's basically that'll be the sum of the d values that you're putting back in there. Gotta set the debiases to 0 because they were uninitialized. Set them to 0. And we're just going through just the rows because there is only one column for the biases or debiases. the I value, the number of rows for the D biases and D values will be the same. You just use one bias for each sample, and then the J values for the columns will be per sample. And then to get the values that you're gonna back propagate to any past layers, previous layers, you'll need the derivatives of the inputs, which is, if you go back to this little example here, A times C. So we had the derivative of the weight was the input. Well, if you just take that backwards, or the other way, A times C, we had A was the derivative of C. Well, if you just want the other version, you could just flip it like this. C times A, we want the derivative of A, that would be C. We need to transpose again. Transpose the weights. And then matrix multiply those weights, the transposed weights with the D values, that chain rule, and that'll get us the derivative of the inputs. So we take all this, we'll come back here, got all this, we created the data here, created our first dense layer, and then we will do a forward pass on that. Of X. And then we'll just do a backward pass on it. Let's do the output for right now. This is not going to be how you end up doing it, of course. This will be derivative values passed back from either a loss function. Well, it would be typically a nonlinear activation, which gets one from the loss function. But the dimensions will fit, so we'll just use this to make sure that everything worked. And the whole reason we're using this little data set here is because with something this small, this few neurons, you can actually watch, print out, and look at the whole process. Especially when we go all the way to handling the optimizer to update the weights, you will be able to see, okay, so we have X, we could see the weights of the first layer, and then how make that matrix multiplication. It's such a small number, you could double check that output is right, and then going backwards, you could double check that everything is right there. You could check it by hand, and then when we have the optimizer in here, you'll be able to see like, okay, the weights before you update them, as well as the derivative of the weights, and then what are the weights afterwards, after they've been updated. So you can see every little piece of the process with such a small data set like this. We'll make sure it all goes through fine. Oh, of course we need to save this. So if you saved it, you would have had a better result than me. There we go. This is the output. For example, this 0.97. I guess the numbers won't really matter at this point. We're just throwing in the output. But yeah, and that is backward pass for the dense layer.